Hello, it's me again. So this time we try to repeat yesterday's talk about functional domain detection and type matching in radare with our Google Summer Code student. So the main goal of this task was to improve the type support, make them more uniform, and support loading from the databases like SDB to store the stuff like Stdcall and function prototypes and so on. Also, it's supposed to be a huge code refactoring with types, with local variables stack, like stack-based, PHP-based, PHP-based for each platform, and also working with a subset of comments or working with variable names and adding and removing them, as well as with variable types. Because before this work, there were variables, but you wasn't able to specify the types. So the change parts are, please switch back. Okay, thank you. The change parts are the T commands and AF commands. And it's also supposed to be able to fetch that information to the radeco, as I mentioned before, to provide extra meta information for the decompiler to improve the type inference. Next week. And the future directions of this task will be integration with the signatures. So we will be able to load the function prototypes from the files, databases with the signatures, like the flags, matters, or signatures internal from the other. And also object-oriented data types, like for C++ or Swift and so on. And also working with exceptions like RTTI, SIG, and so on. And also, of course, it's supporting of the loading function types from the mongo string of the function, and loading information from the dwarf PDB or in load for the macros. So the main part of the talk will be an example and description how the comments for the working with the types and local variables are done. So the next part.
Hello everyone.
Hi.
This is oddcoder from Egypt. I'm a junior computer and digital communication engineering student with variable interests in system software and malware exploitation and that stuff. I am also happily part of radare2 development team and a participant for Google Summer of Code of year 2016. And actually I passed this year. So, before I start, I'd like to thank all of those who have helped me for the over past couple of months, especially my parents for their love and support. Of course, I'd like to also point out the tremendous amount of efforts made by my mentors, both Volka Pancake and of course Majan. Their efforts really, without them, project was never gonna finish in time. And I'd like to tell them thank you. So, the problem I was trying to solve was to implement a way to detect formal arguments and local variables. And by detecting, I don't mean just detecting them, but also changing their names and types, and pretty much what they call it, manipulating arguments and local variables. And by the way, I will use the terminology variable for both formal arguments and local variables from now on. Also, what the second part of the task was to gather type information about those variables, and that's it. Actually, I did a few bunch of smaller tasks, like the one I really loved was adding colors to 2048 game, which I really love playing. So, the do and to-do lists. Actually, I was not supposed to use constraint solver like Z3, for example. Why? Because it was already implemented in radeco side. So if I would need to use a constraint solver, it would be better to do it in Rust there instead of duplicating the whole same implementation stuff in C. And of course, I didn't know Rust at that time. So I'd have to learn Rust just to do that, and I didn't get enough time for this. One other thing was not using debugger. This may sound normal, but in fact, there was certain pieces of information, especially for the type matching, that was never going to be available without debugging or, well, just debugging, like information about the imported function, how their stack frame is formed, and this stuff. Also, two more important things was to make the code architecture independent. I mean the target architecture for the binary I'm going to analyze. I only know x86 at that time, and I really wanted it to work for every other architecture. And of course, I wanted it to be easy to extend and modular. For a simple reason, many programmers are lazy, just like me, and if they found things very complex to improve, they will just rm-f and re-implement from scratch. And I wanted to avoid that as much as possible. Well, so the challenges I have faced during the implementation process was that everything got a piece of it implemented somewhere, and I had to decide whether to re-implement from scratch or refactor and extend. And that was not an easy decision to take. Many things I took the wrong decision at the beginning and just refactored and extended it. Then later on, I realized, well, it would have been better if I just created it from scratch. Also, this is the first time for me to work on a very large code base such as radare. Most of my previous projects were school projects that are at max a couple of files, and that's it. This project was really big with many things that I never heard of, like the convertive, or what they call it, static code analysis and testing suites. I also had to learn a lot of things on the fly. Well, I just learned it till the amount of knowledge I need to get the task finished, and I forgot it, but it was how things got done, and it was good. Also, I was very stressed at the very beginning and was worried if I couldn't make the project work. Actually, this stress was revealed as time go on, and it started to be changed into happiness with the amount of work I was able to accomplish. So, the old implementation of the function arguments and locals. For the first part, it was already partially implemented, but got few drawbacks, like it only worked on x86. I guess only 32-bit binaries, and there was no really local variable in the sense of across the whole binary file, you can only get one variable called x. If you created x in a function foo and x in another function bar, it will just override the old x. And after all, you will get one just variable with that name. Also, there was no variables that are offset from the stack pointer, or variables that are offset, not offset, but register-based variables, such as those used for fast code. It was only base pointer, or let's say EPP, because it will be only for Intel x86. So, what I try to do is to make it on the work on other architectures side by side with x86 32-bit. You will also see our demos will be based on 64-bit x86. Also variables and locals. Also variables are locals to their function, so we can only have one variable I for one function. But I mean we can have multiple variables called I for different functions. So things became local. Also, I added support to the stack pointer-based variables and the register-based variables that works side by side with the old base pointer-based variables. Currently, automation only works for the base pointer variables and stack pointer-based variables, not for the register variables. But it will be work in progress soon, I hope so. So, this is the old version of radare to see the quick difference. You can locate the RBP minus then hex offset. If in the new version, you will see it goes at the very top, variable int local underscore blah blah blah, and they are used downward. You can also rename those variables to whatever you want, change the data type, and also display the value stored in these variables while debugging or at emulating. This is not limited to basic data types, but also for complex ones such as structs or unions, even nested structs. I guess it will work fine, never been tested before. So how does it all work? Full string matching on ESIL. It heavily relies on ESIL. When I implemented this first, I didn't know well enough about ESIL, almost zero knowledge on the APIs. I just realized that I can do regular expression matching on the strings for the local variable. But of course, I didn't know how to do regular expressions with radare2 APIs. So I went for substringing and trimming strings in ESIL, and it worked pretty well. First step is to locate the candidate var. Candidate var is one of three basic forms, either number followed by comma, then SP. Well, it's not really SP. First of all, we just grab the stack pointer name from our register profiles, and we put it into that string, and we try to find an SP followed by plus and number before it. Same for the other two forms. Once we find one of them, we will ensure that it will be obviously a local variable or function arguments. Here comes a problem. Due to the commutative property of the adding operation, we can switch number and stack pointer or number and base pointer in case of plus. So it will just produce the same value. So for some architectures, it won't work this way until you change the ESI enter to produce the right order of things. It will be really easy, just a couple of lines edit, and it will work. Please, by the way, if anyone wants to add this support to any architecture that he needs, just feel free to tell me. I'm available on the IRC of radare as well as Telegram. So next step is to identify the type of candidate var. By type, I don't mean integer or float or double. I mean whether it's a local variable or function arguments. At this point, really, we don't reject any candidate var. All of them are accepted. Maybe in a further step, I will plan to how to say this is false positive or false negative, that stuff. So we get a number followed by a base pointer followed by plus, then it's an argument. Number followed by a base pointer followed by a negative, then it's local variable. The problem is when we get a number followed by a stack pointer followed by plus. Actually, because the fact that stack pointer is really at the top of the stack, I mean it goes downward, of course. Everything is just above it, both arguments and variables. Due to this, we will need to follow another technique to identify the type of this variable. What I did is really depending on the stack frame size, it's calculated by the general AF command. It's stored somewhere in the analysis structure in radar source. I just grab this stack frame size, and if the offset from stack pointer is above it, then of course it's too far to be inside the working area of the function, so it's argument, otherwise it's a variable. That's simple. The last step, it's the simplest one of them all, is to rename. Setting names and registering the variable. At this step, every data type defaults to an integer. Names are very simple. For local variables, we put local underscore the offset in hexadecimal followed by an H. In case of variables, we put R underscore and the number followed by an H. This underscore counter is not used unless two variables got the same name. For example, we have an EBP minus hex10 and ESP plus hex10. Assuming both of them are local variables, then both of them should be named var underscore 10h, right? Well, no, that won't happen because actually naming here is used to identify variable. You can set variable types only by name, or variable renaming variable also you use the name, so it should be unique with the same function. So one of them will be renamed var underscore 10h. On the other hand, the other will be renamed var underscore 10h underscore 2. So I guess we're going a bit quick here. Okay. The second part of my task was implementing type matching. As I said, for until the first part, every data type will be default to an integer. But what I will be trying to do here is to grab the data types from known functions, such as libc functions or Windows APIs. Actually, just knowing the function won't really help. You also need to know about the calling convention of that function. Be able also to trace the instructions and of course trace back, so we can identify what instructions are exactly those used to set up the parameter list for that function. So, what's a calling convention? It's the most important part in my implementation, where when it works, everything else will work. If it gets broken, then bad things will really happen. There are many calling conventions out there, like this C declaration or Stdcall, which is standard on most Linux systems, 32-bit x86 machines. Arguments are pushed right to left. Return values put in EAX, and the caller cleans the stack. Actually, finding out who cleans the stack would be a bit problematic because based on just the function name, we can't identify whether the caller or the company is the one who cleans the stack. And this will be a problem because if the caller cleans the stack and we clean the stack of functions that's never executed, it will mess up everything. So we should just avoid executing this instruction. If you got a simple mem set like this one, and we want to see how arguments are aligned into memory, the hex 100 is pushed first, right to left, then the character A, then that memory address, then call to memset. What's not shown here is there will be at the bottom clean, which will add some offset to stack pointer. We don't really want this instruction to execute because it will just mess up the whole stack frame for the caller function. The reason it doesn't mess things up in real life because that memset will be executed. But here we are not debugging, we are emulating, and imported functions never get emulated. The second popular calling convention is for 32-bit machines, of course, is Stdcall. Also, I guess I read it once called Windows call. Arguments are pushed exactly the opposite way, left to right. Return value is also put in EAX, and of course, if it's bigger than 32-bit, it's put in EDX, then EAX. However, here the clean function is the one which cleans the stack frame. The same memset will just, you will see things aligned differently into the stack. The literal will be pushed first, then the character 80, then the hex 100, then we call memset. But here, it just complete the way it is. There will be no clean instruction. Also, there is yet another calling convention, the Windows API for x86, which is totally different. Stack at all. Arguments are pushed into RCX and RTX, R8 and R9. And if that's not, someone said something?
It was just a temporal connection from phone, please.
Okay, I will go ahead. And the return value is put into RAX. And of course, there are much more calling conventions that exist in life. Arch-dependent calling conventions and calling conventions that's limited to certain programming language, or calling convention that's even limited to certain compiler family. And of course, custom calling conventions that are used by manual people. And I wanted to keep all of this in mind while designing a system that will use the calling convention independent of the function to figure out how elements are, how arguments are placed into order to be passed to the calling function. So, why do we care? The reason is we need to be able to define a new calling convention whenever possible, unloading useless calling convention, and instead of hard coding the whole calling convention, I tried to isolate the data from the code, and I assumed that the calling convention and all its specifications, like how arguments are passed, who cleans the stack, are part of the data. The code just manipulated and translated. It's stored in an SDB database with good documentation, really, on GitHub repo for radare. So, some things quickly before I get deep into implementation. As I said, first we got something like this: no variables detected, nothing at all. Then after the AFBA analysis round, we got those var int local, and it's renamed automatically. But at this analysis round, and by the way, it's not done automatically by either AA or triple A's or 4A's. You just need to launch it manually. This is the target. You see here, right before the turbulent function, it identified RDI as the first argument, and it's of type constant characters pointer. Same for malloc. Even the interesting one is this string copy. Right there at hex 4006A, it identified the first two arguments right before it. Then the third one is separated between the second one by like 4 instructions. I'm really happy that it got it correctly. So, how does that all works? It's pretty much emulating. You just read the next instruction, which happens here to be the first instruction too. Then once it reads it, it records that instruction for tracing back. It stores the instruction, the offset of this instruction in the binary file, so we can repeat it again. After that, it emulates the instruction and stores all the register accesses as well as memory read and writes. So we can identify the instruction. And for example, let's say that we know that the command we're looking for is the one that writes into RAX. So we would look for the traceback first command that writes into RAX, and this command is the one that edits the first argument to the function, whatever we're calling. And it goes over and over, but whenever we find a call instruction, things take another path. Actually, this part really links to a bunch of small tasks that I didn't mention here, and to get things work, I was really lucky that everything just fit in place and it worked. First thing, we grab the function definition from types database, like it's stored in some sort of parsed structure in another SDB database. Once we get that, we go for the function calling convention. We grab it from the calling convention database too. Then we do some math to calculate the location of the argument. Once we calculated the location of the argument, whether it was a stack-based or register-based, we then search through the whole trace log we stored before for writing into these locations. Once that was done, it's really up to us to do what we want at this point. We know that the instruction X is setting the nth argument for whatever function we want. Let me go back a bit. Yep, here. For example, in the first Sterling example, we know that the previous instruction is the one setting the argument for Sterling. Now we can do whatever we want. For me, at this point, I just added a comment here with the name of the argument. I just grabbed that from man pages. And if this argument is, if it happened that this instruction accesses a variable, whether it was argument or local, like the argument is local underscore 20h, it will just set the type of this local variable to be the type of the nth argument, which is here the first argument of student, which will be constant char star himself nth. Now showtime. I hope that Stdcall will show you some demos we have prepared together.
Sure. Because we need to perform the analysis of the binary and go to the function which we are going to add the analysis of the types. And here you can see the TK comment, which was added by oddcoder, and it simply define the types of the function with the internal SDB format, so you don't need to add the manually. As you can see, it's a function, but for example, it defines the return type, size t, and it also defines the calling convention, MD64 in this case. And also it defines its arguments. First, first argument, and it also defines the count of the arguments. And after defining a types for a few functions like malloc, store copy, and free, we perform the analysis of the binary with using ECU. So we add the ECU information about ECU emulation, and then perform the deinitialization of the function. Let me show you that in radare. Oh, it was disconnected.
But it's okay.
Okay. Okay, you're back. Hello?
Hello?
Okay.
Yes, I'm back.
So I'm showing you the demo.
Okay.
So here we can see that after that we performed the analysis, and after we added the function types, it determined as the first argument string for function paths, and mark it as a string and show the string contents. The same was done for the string copy. Here we can see the crux and RCE marked as variables with a char pointer type. And we can see obviously that it's marked as an source and destination arguments, like it was done in some article I don't want to talk about. So simply you can see the result. It's quite useful, especially if you have a big database of the standard functions, and you can help to build it, the center code request. You're welcome. And if you have any questions, please ask. I think it's all. Oddcoder?
Yep, I'm here. So, any questions?
And the register-based argument.
They are already added, but you need to specify the calling convention. And if it's not standard convention like Stdcall or GSoC, you just need to add a calling convention description. When you
It will work in any architecture.
What?
It will work on any architecture.
yes.
Will it work when there's multiple instructions without me?
Oh, this is a simplest types inference technique, and for the most complex, we will need radeco because it should involve the mathematical model and graphs theory and so on. So this is the simplest part, so we can do this in the radar itself. They don't need to install everything extra. So it's a compromise. If you want to the simplest analysis inside the radar, this should go. But if you want military grade decompilation, radeco should do the job.
So you need to implement the code connection. And for the that's the file you need to modify to add a new function in for the detection. So again, really simple. It is for example, this is for ASICs and 4. So you just need to know a bit of parsing and parse all the manual doc, and you will have all you don't even need to know reverse engineering to do that. It's simple. Everyone can contribute.
So, any more questions? So I think we should go to the next talk. Thank you, everyone. Thank you for